Hello, in this video I'm going to share with you the design and test of a do-it-yourself solid-state relay used to replace a electromechanical relay. So this is the electromechanical relay and the solid-state relay. This is do-it-yourself. It comes with a low voltage cutoff. You can program the low voltage cutoff. This one is dumb. It just connect or disconnect. It doesn't have the low voltage cutoff for the factory version. So let's take a look at the circuit diagram of this. So it basically have three components. You have a programmable low voltage cutoff relay, and the relay would drive the optocoupler, and the optocoupler is hooked up to a p-channel MOSFET, and this p-channel MOSFET spec is IPB180P04 P4L-02, and this is designed for 40 amps of DC current, 40 amps. So let's take a look at the M609 low voltage cutoff relay, and this is the setup, the relay, and also the optocoupler. And right now the voltage is 10.7, and if I hit the left button, the plus button, it shows you the cutoff voltage. So the cutoff voltage is programmed to 11.8. So 11.8. And this is the recovery delta voltage, also programmable. Is 0.8 volt. So the recovery is 0.8 volt. So we have 11.8 cutoff plus 0.8, so 12.6 it will recover. So let's adjust the voltage and see what happens. So this is 11.7 is still off. Now it's 12.7. It just came on. Let me turn it off again. 11.7 turn off. 12.7 turns on. So this is very simple and useful. In my particular design, I actually removed the relay on this board and hook up the optocoupler directly onto the circuit, the coil that drives the relay. So it truly has no electromechanical part in my design. So I took off the relay and put in the input of the opto isolator into the coil driver. And the only change I need to make is change the 2.2K to 330 ohm, because this board is for 12 volt and the driver is only 5 volts. So I changed that to 330 ohm for it to work. And this is the whole circuit diagram. Okay, whole circuit diagram for up to 40 amps. And the setup I have is I have a battery, and battery positive is connected to the solid state relay, and the solid state relay go to the inverter. And then I also have a shunt to measure the current feeding into the inverter. This is the shunt meter. And then when it come back to the negative, and the negative is connected to a JK-BMS. And the low I have is a 100-watt light bulb, and also a dehumidifier. So let me turn on the low. So the low is on, and my JKBMS app shows the currents of 37, almost 38 amps discharging, almost 38 amps discharging. And my shunt meter, which is more accurate, shows 40.6 amp of discharging. 40.6 amp, my shunt meter. And the single MOSFET is mounted on a couple of ring terminal connector. I flattened it out. These are 60 amp ring terminal connector, and I soldered both sides. And this is the board. And let's measure the temperature of the MOSFET, and which is a very important design requirement. Let me measure it in Celsius. So the Celsius temperature, so the temperature is rising. It's 34 degrees Celsius, and earlier I actually measured the temperature when this is completely steady state and warm. And let me show you the measured temperature earlier. And the temperature is actually 47 degrees Celsius. 47 degrees Celsius. And the voltage drop between the drain and the source, or the input and output, is 84.7 millivolt. 84.7 millivolt. And again, the shunt meter is 40.6 amp, and the JKBMS internal current sensing is 37.6. 37.6. So there you have it. Very simple design, and it's used to replace the electromechanical relay, and this is good up to 40 amp. In my application, it's less than 30 amp, so this is good for 40 amp, and with quite a bit of safety margin. And it also comes with a switch. I could switch it off, and it will shut everything off. Okay, I just switched the relay off, so now everything is shut off. So thank you for watching. Have a good day.